Hello, this is Arjun, Assistant Professor, Department of Mechanical Engineering, VIDYA Institute of Technology. In this session, we'll see how to solve the problems related to trusses. And this is an example problem I have taken. In this, determine the nodal displacements for the truss subjected to the loads as shown in figure. They are given two elements, element 1 and element 2, with the nodes and loading parameters. So let us see how to solve this problem. Now this is element 1, this is element 2. As element numbers are given, I will write the node numbers. Now this will be node number 1, this will be node number 2, and this will be node number 3. At node 1 we will have two displacement functions, that will be q1 and q2. At node 2 we will have two displacement functions, q3 and q4. Similarly, at node 3 we will have two displacement functions, q5 and q6. Now let us write the coordinates for node 1, node 2 and node 3 respectively. Now this will be a reference node, so the coordinates for node 1 will be 0, 0, and the coordinates for node 2, from this reference point, the distance of node 2 from this origin point is 1 meter. So x distance is 1000, 1 meter. I will represent that in mm, 1000. Y distance is 0. So node 2 coordinates will be now 1000, 0, and node 3 coordinates are, so x coordinate is 0 and y coordinate is 1 meter. So node 3 coordinates will be 0, 1000. Okay. Now in order to solve this problem, we need to write two data. One is called as nodal data. Okay. In this nodal data, so we will write the number of nodes present in this. So in this particular segment, truss segment given, we have three nodes, node 1, node 2 and node 3. So I will write like this: node number, x coordinate and y coordinate. So now write down the number of nodes present in this. So node number 1, node number 2, node number 3. So if we consider node number 1, x coordinate is 0 and y coordinate is also 0. So write that values here. X coordinate is 0 and y coordinate is 0. At node number 2, this is a node number 2, here x coordinate is 1000 mm and y coordinate is 0 mm. So write x coordinate value here 1000 mm and y coordinate value is 0. And for node number 3, this is node number 3, x coordinate is 0 and y coordinate is 1000, x coordinate is 0 and y coordinate is 1000. This is a first table called as nodal data. Why we are representing this nodal data is, so it will make us very easy for further stages of problem analysis. And now I will write one more data called as element connectivity table. So now I will write element connectivity table. So in this element connectivity table, we write like this. First is element number, okay. Now I'll write element connectivity table here. So we write element number, initial node, final node, length of the element can be represented as LE, L, we write direction cosines L, M, L into M, L square, M square. So this 3 L into L square, M square, these are optional, and if you represent this in a diagram in this particular table, it will be helpful for you to solve the problems very clearly. So now I'll start from this initial process. Now element number is 1. So element number is 1. So this is element number 1. And see, if you observe this initial node and final node. So the initial node is the starting point. Okay. Now this is the initial node. So node number 1 is the initial node for element number 1. And node number 2 is a final node for element number 1. So element number 1, this is a starting point and this is the ending point. Okay. And node 1 coordinates. Okay. The coordinates for node 1 are 0, 0. Similarly, the coordinates for node 2 are 1000, 0, as we have written nodal data. Okay. Node number x, y. So node number 1, 2, 3, x coordinate was 0, y coordinate was 0. Node number 2, x coordinate was 1000, y coordinate was 0. Node number 3, x coordinate is 0, y coordinate was 1000 mm. So now if you want for your reference, you can write like this. Node 1 coordinates are 0, 0, and node 2 coordinates are 1000, 0. Okay. And now element number 2. So totally we have 2 elements. Okay. Element number 2. So for element number 2, now this is the element number 2. Initial node, that is starting point for element number 2 is node 2, and the final node for element 2 is node 3. So initial node is node 2 and final node is node 3. So initial node coordinates, okay, initial node 2 coordinates are 1000, 0. So you can if you have written the nodal data, now it will be helpful for writing this initial node and final nodes. So initial node is 1000, 0, and final node 3 coordinates are 0, 1000. So you can write like this: 0, 1000. And see, now if you want, in order to find out length of the element, okay, the formula used to find out length of the element is LE is equals to square root of x2 minus x1 whole square plus y2 minus y1 whole square. Okay, this is a formula used to find out length of the element LE. So now we need to find out length of the element for element 1, element 2. Then we can find out direction cosines L, M. Once you get the value of L and M, if you multiply these two, you get this value. Square root of this value will be L square and M square. So now we will consider for element 1. When you consider element 1, okay, so now for instance you can write like this. You can treat this as x1, and you can treat this as y1, you can treat this as x2, you can treat this as y2. Okay, one element. So x1, y1, x2, y2 for element 1. So these values you can substitute into that final equation, which is the length of the element. Okay, once you substitute into that final equation length of the element, you will be getting the value of LE. So now LE can be written as so now value of x2 is 1000, x1 is 0, so this will be 1000 minus 0 whole square, and value of y2 is 0 and y1 is 0, so this will be 0 minus 0 whole square. So length of the element will be 1000 mm. So that can be written over here. Okay, length of the element is 1000 mm for this case, and this direction cosine L can be written as x2 minus x1 divided by length of the element. Now x2 minus x1 is 1000 minus 0 divided by length of the element is 1000. So length of the element, direction cosine L value will be 1. Similarly, m direction cosine m will be y2 minus y1 divided by length of the element. So y2 minus y1, 0 minus 0 divided by length of the element is 1000. So anything divided by 0 will be 0, 0 divided by anything will be 0. So your direction cosine m will be 0. And if you multiply these two values, L into m value will be 0, and L square value will be square of this value, it will be 1, and square of this value, it will be 0. So similarly you can find out for case 2, again for case 2, for element 2, also you can find out length of the element using the same formula, and direction cosines L and m. If you find out the length of the element will be 14.21, and your direction cosine L will be minus 0.7071, and direction cosine m will be 0.7071, and product of L into m minus 0.4999, and L square of this value, again this will be 0.4999, and m square, again it will be 0.4999. Okay. So now we have element connectivity table and nodal data. So now I have erased the nodal nodal data table. So since we know that the stiffness matrix for a truss element stiffness matrix is given by EA by LE, L square, LM, LM, M square, minus L square, minus LM, minus LM, minus M square, so minus L square, minus LM, minus LM, minus M square, plus L square, plus L into M, plus L into M, plus M square. Now this is the stiffness matrix. The reason why I suggested you to write L into M, L square, M square values in this table is, so if you write all these values in the table initially, so we would have all these values directly itself, and there is no probabilities of your problem going wrong. And now in this stiffness matrix equation, you can directly substitute the values. So that is what I will do now. We have given with Young's modulus 70 GPa and area 100 mm square. So now I will take the values. So now element stiffness matrix. So E is 70 GPa. So I will convert that into Newton per mm square. 70 into 10 power 3 Newton per mm square. Area is 100 mm square divided by, now when you are finding out element stiffness matrix for element 1, KE1, okay, length of the element is 1000 mm. The length of the element is 1000 mm. Now you can write, we have all these values. L square is 1, L into M is 0, M square is 0, so L square is 1, L into M is 0. Again, okay, now we'll continue with this one. So you can observe this, these 4 elements have positive values and these 4 elements have negative values, and these 4 are similar to this 4, so I'll write directly. So minus 1, 0, so if you want you can note down here. So L square is plus 1, so we have minus L square, so minus 1, 0, 0, 0. So minus 1, so now this 4 are similar to this 4, so I will write directly 0, 0, and plus 1, 0, 0, 0. Okay, and so now we can simplify this value, 70 into 10 power 3 into 100 divided by 1000, and if we simplify this value, so we'll get 0.7 into 10 power 4. So what I'll do is I'll keep this power outside, which is 10 power 4, and I'll multiply this 0.7 inside, and I will rewrite this matrix like this. So 10 power 4, 0.7, 0, minus 0.7, 0, 0, 0, 0, 0, minus 0.7, 0, 0.7, 0, 0, 0, 0, 0. Okay, now for your reference, so since element 1 is made up of node 1 and node 2, and each node has 2 degrees of freedom in trusses, so at node 1 we will get 2 nodal displacements Q1 and Q2. At node 2 we will get 2 nodal displacements Q3 and Q4. So element 1 consists of nodal displacements Q1, Q2, Q3, Q4. For our reference, we will rewrite this as 1, 2, 3, 4, 1, 2, 3, 4. Now this is the element stiffness matrix for element 1. So similarly now I will write a stiffness matrix for element 2. So we should keep in mind whatever the power that we take outside for both the elements has to be same. So just 10 power 4. Here also I will take 10 power 4 outside, and by substituting all these values, if we simplify, this is the stiffness matrix, what we will be getting 3.4994 minus 2.474 minus 2.474 plus 2.474. So now the other will be opposite to this, so 3.4994, so minus plus 2.474, 2.474 plus minus 2.474, and now this will be quite opposite to this. This will be similar, so 3.4994, 2.474, 2.474 minus 2.474, and now this 4 elements will be similar to this, minus 3.4994 minus 2.474 minus 2.474, 2.474. This is element stiffness matrix for element 2. See, now you can see from this diagram, element 2 is made up of node 2 and node 3. So node 2 has nodal displacements 3, 4, and node 3 has nodal displacement 5, 6. So for our reference we can write like this: 3, 4, 5, 6, 3, 4, 5, 6. So now since we have both the element stiffness matrix, now we'll try to find out global stiffness matrix. So I'll write like this: K is equals to, I'll write the power outside, 1, 2, 3, 4. Pause. Now I will derive the global stiffness matrix. So written like this: 1, 2, 3, 4, 5, 6 for our reference. This is for reference, the numbers I will written. Okay, now 1 cross 1, this is 1 cross 1, 0.7. So 2 cross 1 will be this one, 2 cross 1, 3 cross 1, 4 cross 1, now 3 cross 1, 4 cross 1. And when it comes to 5 cross 1, so this is a nodal displacement 5, that is which comes in node 3. Node 3 is not directly linked to node 1. So 5 cross 1, there will be no element. So now I will write 1 cross 1 is 0.7, 2 cross 1 is 0, 3 cross 1 is minus 0.7, 4 cross 1 is 0, 5 cross 1 0, 6 cross 1 0. So now similarly 1 cross 2, you can see 1 cross 2 is 0, 2 cross 2 is 0, 3 cross 3 is 0, 4 cross 2 is 0. So 0, 0, 0, 0, 0. 5 cross 2 is also 0 and 6 cross 2 is also 0. Now when it comes to 1 cross 3, minus 0.7, 2 cross 3 is 0, 3 cross 3, now we should be careful here. So when it comes to 3 cross 3, we have 0.7 here, and again see, you can observe 3 cross 3, we have one more value here. Now you need to add these two values, plus 0.7 minus 3.4994, so it will be minus 2.7994. Okay, now 4 cross 3, now this will be 4 cross 3 minus 2.474. 5 cross 3 is this value, 3.4994, and 6 cross 3 is 2.474. Okay, now 1 cross 4 is 0, 2 cross 4 is 0, 3 cross 4. Again, when it comes to 3 cross 4, again we will have two values here. Okay, that is 3 cross 4 will get one value here and one value here. Similarly for 4 cross 3 and 4 cross 4. So 1 cross 4 is 0, 2 cross 4 is 0. So again 3 cross 4 will have minus 2.474. Okay, and 0, since it is 0, so we need not to add these two values. If you get some values here, we are supposed to add these two values. So it will be minus 2.474 and 4 cross 4. So this is 4 cross 4 plus 2.474 and 5 cross 4, 2.474, 6 cross 4 minus 2.474. Now 1 cross 5 is 0, 2 cross 5 is 0, 3 cross 5, this is a value 3.4994 and minus 3.499, sorry, this is 2.474 and this value is minus 3.4994 and this is minus 2.474. 1 cross 6 is 0, 2 cross 6 is 0, 3 cross 6, so 2.474. This is 3 cross 6, 4 cross 6 minus 2.474, 5 cross 6 minus 2.474, 6 cross 6 is minus 2.474. Now this is a global stiffness matrix. Now once you write the global stiffness matrix, we have to relate this to the general description of FEM. Now I will rewrite the functions here. We have 6 nodal displacements which are to be found out. Okay, and I'll write the forces F1, F2, F3, F4, F5 and F6. So each node will have 2 degrees of freedom. So if we observe node 1, there are no forces acting on this. So x displacement is q1, y displacement is q2. Similarly, F1 will be the force which will be acting in x direction and F2 will be the force which will be acting in y direction. Since this node is totally fixed, there is no load acting on node 1, node 2, so its values can be taken as 0 and 0. And when it comes to node 2, and x in the x direction, there is a load of compressive load of minus 100 kilonewton. So F3 will be minus 100 Newton, and there is no load in y direction, so F4 will be treated as 0. And when it comes to node 3, there is no load in x direction, so F5 will be 0, and there is a tensile load of 200 Newton in a y direction, so it is taken as 200 Newton. So now this is a global stiffness matrix. Now we have to solve using the elimination method. See, we're using elimination method. Since node 1 is totally fixed, we have two displacement functions. I will delete first row, first column, second row, second column. Okay, and when it comes to node 2, Q3, Q4 both are free, so we'll leave it as it is. And when it comes to node 3, okay, see it is fixed in x, the roller is given in y direction and x displacement is fixed. Okay, roller is given in y direction and x displacement is fixed, so that means it is free to move in y direction, whereas this x displacement is fixed. So I'll delete this particular value. As I told, y direction is free to move and x direction is fixed, so I'll delete fifth row, which is pertaining to x, and fifth column. So and if we solve, these are the values left out: 1, 2, 3. Okay, this is a 1, and this value. So we would be getting value of Q3, Q4 and Q6. Pardon me, there was a mistake. So actually this node was fixed in y direction and it was free to move in x direction. So the roller support was given free to move in x direction, and regarding to that, that x direction is left as it is, and the fourth row, fourth column is deleted. So we'll be getting Q3 and Q6, and if we solve this equation, the value of Q3 will be 37.928 and value of Q4 will be 42.91. So all these dimensions are in mm. This is Q6 and Q3. Okay, this is how we should find out nodal displacements for a truss element. Thank you.